band bending occurs because there's a non-uniformity in the amount of charge. So imagine you create an area with high p-type doping and high area of high n-type doping. What happens is when those two areas combine, you get a diffusion of free carriers, which creates built-in charges. That built-in charges changes the local Fermi energy, changes where the electrons and holes sense. So therefore, it changes the local Fermi energy level. We use band bending to determine the directions in which electrons and holes would prefer to flow. This is very important for both chemistry and for devices. So consider an NP-N silicon homo junction. What you see here on the left is an N-type, in the center is a P-type, and on the right is an N-type device. You always start with drawing your Fermi energy level. So you draw it flat whenever you're dealing with a homo junction. Then you draw the flat band regions in the areas relative to where their doping is. So in the N-type region, you can see that I drew the conduction band closer to the Fermi energy level. And in the P-type region, I drew the valence band closer to the Fermi energy level. The Fermi energy level is flat. I draw it flat. And I'm representing the band bending as a change in the amount of conduction and valence band energy. This is just a convention. It's not necessarily how it works physically, but this is a way in which we interpret the built-in forces within the material. Now, once you've drawn the flat band, then what happens is whenever you have this, it behaves like a continuous function. So then you connect the different areas in which you create is the band bending response. From that band bending response, you have to remember that electrons prefer to move from higher energy to lower energy. Prefer to move from electronegative to electropositive. And electropositive is lower in the energy level. And vice versa with the holes. The holes like to go up. They like to go to electronegative, higher energy levels. And so based on that, you can see the electrons will prefer to flow from the p-type region down into the n-type region on both interfaces. And the holes like to flow in the opposite region. And so from this, we can learn stuff about the built-in charges at the interfaces. We know the only thing that moves free carriers are charge. And so that, only thing that moves free carriers is electric field. And so what that means is that if my electron is moving away from this region, from the right part to the left, that means the right part must be electronegative compared to the left part, because we know electrons prefer to move away from negative charge and towards positive charge. So we can use this direction of the electron hole flow to determine how electronegative or positive a particular region in a semiconductor is. Remember that in the flat band regions, it means that there's no buildup of charge. Okay? There's no buildup of charge. And that's why they call it the flat band region. There's no band bending there. And then you can see that if I take my electric field ends up being the derivative of my charge. And so when you take the derivative of my charge, derivative of my energy, I find that in the flat band regions, I get zero electric field. And that my electric field is always the highest at the junction. So that's something to remember, that the electric field is always going to be the strongest at the junction. Now sometimes what you have is what's called hetero junctions. In hetero junctions, it means that you have two different types of materials. So sometimes you might not have an N and P type material, with just both being silicon. The P-type material might be a completely different semiconductor than the N-type material. In this case, consider P-type gallium arsenide with N-type gallium nitride. For us to draw this band bending scenario, what we want to do is we want to consider the difference in the band offsets. Now, the band offsets occur based off the electron affinity. Electron affinity tells me how much energy is between my vacuum level and my conduction band. So when you start, you want to draw a flat vacuum level. So you draw a flat vacuum level, and I'm drawing my interface. Then on the left side, on my gallium arsenide side, I know my electron affinity is 4.07. So I'm going to draw my conduction band 4.07 eV away from lower than my vacuum level. Then I know my energy band gap is 1.42. So I'm going to draw 1.42 energy away from my EC, and that becomes my EV. So you can see that I've now drawn my EC and my EV levels. Now on the right side, I have gallium nitride. Here, my electron affinity is 4.1. Because it's 4.1, we know my EC is going to go a little bit lower than the EC on the left side. And I know my energy band gap is 3.4. So I'm going to draw my valence band much lower comparatively to that on the left side. Now we want to sketch this and try to make this as accurate as possible. Graph paper is ideal to make sure that you're within a reasonable scale. But I'm just kind of eyeballing this. So it might not be perfect. So once you draw your conduction and valence band on both sides, right? That's pinned there. Then what I'm going to do is I'm going to draw my Fermi energy level as flat. And I'm going to try to draw it through both bands, both band gaps, right? So through my left band gap and my right band gap. And then far away from the interface, I'm going to draw my flat band region. So on the left side, I know my energy band gap I drew about this wide. So I want to draw it the same width. And I want to draw a p-type. So my Fermi energy should be close to my valence band. And I made it really dramatic. So that way you can really see the band bending. And on the inside, again, I drew my conduction band really close to my Fermi energy level. And I made sure I accounted for the fact that I have a very, very wide band gap. Once I've drawn my flat band regions, I can now connect my flat band region to my pin regions as such. And hence I can see my band bending. Then I can clean it up a little bit and I'm able to see how my holes and electrons prefer to flow. There's a huge acceleration of holes going from the gallium nitride to the gallium arsenide, right? But there's a slight acceleration of electrons to do the same thing, as you can see. All right. However, as you can also see, it would be very difficult to get holes from my gallium arsenide to my gallium nitride, and electrons from my gallium nitride to my gallium arsenide, but particularly for the holes. And so what this means is that this is going to be very rectifying for hole flow.